Effect of cold joint on stratified slabs. Abstract stratified slab consists of two or more types of concrete, in particular, of composite materials consisting of high-strength concrete, HSC, and normal-strength concrete, NSC. This study had the effect of delay time overlap between two concrete mixes, 15 minutes and 60 minutes. An experimental program was conducted to investigate the flexural behavior of two HSC/NSC slabs that had subjected to double static loads. The most important achievement conclusion is the success of the idea of casting different strengths concrete layers, using a short time, 60 minutes, interval to improve the flexural behavior of the slab. Keywords: composite slab, multi-layers concrete, high-strength concrete, effect of cold joint. Introduction: the usage of HSC has been risen in the past decades, to enhance structural element and retain the volume of structural elements. The usage of the NSC may lead to larger volumes of concrete, which results misleading in the cost of structure. On the other hand, the usage of only HSC may lead to overestimated cost to an ordinary structure. As a result, the concept of using NSC with HSC or any advanced concrete to obtain the benefits of two materials is developed. The lower layer was cast by NSC, 25 MPa, to reduce the cost, but the upper layer of compression zone was cast by HSC, 60 MPa, to enhance the behavior of concrete slabs in both flexural and deformation. A lot of studies had the impact of the time delay when casting the second layer of concrete on its mechanical properties 1, 2, 3, 4, 5, 6. Their results indicated that when cast the second layer of concrete at early age, about 1 hour, the compressive, flexural, and split tensile strengths decreased by neglected ratios. So, this study will show the flexural behavior for composite sections, HSC/NSC, by taking short time lap, 15 minutes and 60 minutes, between casting the two layers. The two times was chosen to study which of them satisfy the good bond between the two layers. 2. Experimental program. HSC mix proportion was done according to previous studies, 7, 8. Trial mix was placed and was tested to ensure required strength. The used concrete mixes were designed to develop a cubic compressive strength of 25 MPa for NSC and 60 MPa for HSC. The concrete mix for the test specimen was made from available materials, which consists of cement content, crushed dolomite, natural sand, silica fume, superplasticizer, and tap drinking water. Concrete ingredients were tested according to the Egyptian standard specifications. 9. The cement used in this research was Sameh 42.5N produced by the Suez Cement Company. Suez Factory. 10. Aggregate was tested according to S1109/2002-11. Silica fume is commercially available through Construction Chemical Company. Visocrete 3425, high-performance superplasticizer was used for the product HSC in order to achieve its required workability 12. A. Steel reinforcement was a high-grade steel B400BR bars of diameters 12 mm and 16 mm. 13. Table 1 to Table 5 show properties of used materials. Two mixes were used to cast slabs, NSC 25 MPa and HSC 60 MPa, and they were designed for target 28 days compressive strength of 25 MPa and 60 MPa respectively. Table 6 show the mix proportions of the two used concrete mixes. The NSC mix was mixed as usual for mixing the ordinary concrete mix in the testing laboratory. In contrast, and due to the low water cement ratio, W/C, in the HSC mix, a special way of mixing the HSC mix was used using a van mixer. Firstly, the fine materials which include cement and silica fume were dry mixed together, then half the amount of mixing water was added gradually to the fines and mixing continues for 2 minutes. After that the superplasticizer was added to the remaining water, then added them to the mix. Finally, fine aggregate was added gradually to the mix, followed by the coarse aggregate, and were mixed continuously for 5 to 6 minutes till the desired workability was achieved. Steel reinforcement cage was arranged and placed in its proper position in the forms. Plastic blocks with 2 cm height were used to keep the reinforcement in its proper position during casting. At the beginning the NSC concrete mix was placed in the forms according to the specific depth and compacted mechanically by internal electrical vibrator. Then after 15 minutes the HSC mix was placed over the NSC mix layer for first slab S1 and after 60 minutes for the second slab. The specimens were cured by spraying water at the morning and the afternoon for 1 week from casting, and then the specimens were left in the ambient temperature until testing. 3 concrete test cubes 150x150x150 mm were cast at the same time with the specimens to ensure exact achieved compressive strength. After the specimens were located under the crosshead of the testing machine, 5 strain gauges for concrete type, PL60-11, with length 6 cm were used to measure the compression strain of the concrete. In addition, deflection at midspan of the slabs was measured by LVDT. Details of test specimens are tabulated in Table 7 and shown in Fig 1. 3. Experimental results. The experimental results of tested slabs were summarized in Table 8, including the load at first crack, PCR, load at first yielding of main steel, pi, ultimate experimental load, PU, deflection at midspan at yielding, delta Y, deflection at failure load, delta F, the maximum strain of concrete at top surface, SC, the maximum strain of main reinforcement surface, SS. The compressive strength for NSC and HSC cubes are 31.3 MPa and 63 MPa respectively as an average of 3 tested cubes. For S1, the load is constant after it reached the ultimate value, but the deflection still increasing until the slab was crushed in compression zone at midspan of the slab. With regard to slab S2, the crushing had happened at the HSC part, so this indicate the full bond between the two layers. Also, it is noted that the ultimate load for slab S1 was lower than the ultimate load for slab S2, so this may be the two mixes were partially mixed with damping method. Fig 2 shows the load deflection relationship of the two slabs. The ultimate loads were 70.15 and 94.91 knots for slabs S1 and S2 respectively. It was concluded that increasing the time overlap from 15 minutes in S1 to 60 minutes in S2, the ultimate load increased by 35.3%. Also, the yielding load increased by 36.6% for S2 than S1. On the other hand, the slab S1 reached to the ultimate load, 70.15 knots, before the slab S2 reached the yielding load, 78.66 knots. So, this indicate the significant benefit for using the HSC in compression zone by using allowable time lap between casting the two layers. 4 conclusions. In this paper, an experimental study was carried out to investigate the structural behavior of stratified slabs. Stratified HSC/NSC elements are appropriate for new constructions and conservation of existing structures. This research concerned on the new constructions by doing the layers at different short time lap between the layers to have good bond between them. From the experimental study, the following conclusions were observed. 1. Stratified slabs was loaded up to failure without sliding between the two layers, so this give more easily constructed method for stratified slabs. 2 at time overlap of 15 minutes, the two layers have partially mixed with them giving lower compressive strength at compression zone. 3 increasing time overlap from 15 minutes for S1 to 60 minutes for S2, the ultimate load increased by 35.3%. Also, the yielding load increased by 36.6% for S2 than S1. 4 the slab S1 reached to the ultimate load, 70.15 knots, before the slab S2 reached the yielding load, 78.66 knots, so, this indicates significant benefit for using the HSC at compression zone by using 60 minutes time overlap between casting the two layers.